In last few lectures, we have seen how to calculate derivative of a function numerically, and we have also discussed the errors associated with the numerical differentiation. In this lecture, we will talk about double derivative of the same function. Recall the function u. We found u prime in three different ways: forward difference, backward difference, and central difference. The forward difference is given by ui plus 1 minus ui by delta x. Backward difference is ui minus 1 by delta x. And the central difference is ui plus 1 minus ui divided by twice delta x. We'll now follow similar procedure to find the expression and the truncation error for ui double prime. For the function u, we can write in Taylor series ui plus 1 equals ui plus delta x ui prime plus delta x square by 2 ui double prime plus delta x cube by 6 ui triple prime, etc. And similarly, ui minus 1 equals ui minus delta x ui prime plus delta x square by 2 ui double prime minus delta x cube by 6 ui triple prime plus additional terms. If we now add these two expressions, we have ui minus 1 plus ui plus 1 equals 2 ui plus delta x square ui double prime plus additional terms. Using this expression, we can write ui double prime equals ui minus 1 minus twice ui plus ui plus 1 divided by delta x square minus additional terms which we know are truncation error, and the first term of the truncation error contains delta x square. That means ui double prime can be expressed as ui minus 1 minus twice ui plus 1 divided by delta x square plus truncation error of the order of delta x square. So this scheme is, as we see, that for finding ui double prime at point I, we have taken ui minus 1 and ui plus 1. So this is a central difference scheme, and this is a second order accurate scheme. You can now go back to this function x square plus 2x that you have already used, and you have tested it for different grid size and different schemes for derivative. Now what you can do at x equal to 0, you can numerically find the double derivative and then vary the grid size and see how the errors will vary with grid size. In next week, we'll talk about how we can systematically develop expression for different derivatives. But right now, in next lecture, we will go back to our Finn equation and we will see that how we can solve the Finn equation. That's all for today. I'll see you in next lecture. Thank you.